Okay, so we'll solve paper 6, March 2021. A student investigates the motion of an oscillating meter rule. He uses the apparatus shown in figure 1.1. So, okay, meter rule is given, stands are given, fine. Part A, the student ensures that meter rule is horizontal. Briefly describe how to check that meter rule is horizontal. You may draw a diagram or draw on figure 1.1 if it helps to explain your answer. The method is quite easy. All you have to do is measure height at different points from the bench. So this is what we are going to write. Measure height of meter rule at different points along the meter rule. If they are equal, the rule will be horizontal. So this is what we are going to write. Remember, whenever you write the answer, do not use too much of the space. If you are running short on lines, just try to write it as close as possible. Don't make long arrows and just write it over here or whatever. I've seen it, students doing that. Well, the papers are being scanned, so there's a specific area which goes for scan. So try to write it as close as possible. Anyway, part B says the student moves the stand so that vertical threads are at the marks on the meter rule shown in figure 1.2. Calculate the distance d between the threads. So this is 2.0 centimeter, this is 98. So we will write 96, but you lose a mark if you don't write 0.0. Reason being least count. I'll just write this as an additional point of meter rule is 0.1 centimeter, meaning always give your answer to one decimal place. C part, he twists the meter rule a small amount as shown in figure 1.3 and then lets it go so that it oscillates in a rotating motion. So, okay, this is rotating and they're measuring time. He measures the time t for 5 complete oscillations of the meter rule. Suggest why it is useful to take a trial reading for this experiment. Um, so we always take a trial reading just to see if the values are measurable. Like sometimes we might take a distance very short or very long, if the time taken is too short, or if it does not freely oscillate. So just to check if time taken is measurable and d values are appropriate, because I cannot tell if I've used an appropriate value until unless I have a trial experiment first. So remember, whenever you have a suggest question, uh, they don't have any specific answer to this usually. It is usually what they do is they give marks for any logical answer, any statement which makes sense, they'll give you a mark for it. So suggests are not necessarily based on some physics that you know from the course or the syllabus. It's just a general idea. Um, for this, you have to visualize the lab apparatus and think of a logical reason. D part, the student carries out the same procedure for values of 20.0, 30.0, 40.0, 50, and 60. His readings are shown. Okay, so d is there, and 1 over t is also there. For distance 20, calculate and record in table 1.1 the value of 1 over t, where t is the time for one oscillation of the meter rule. Use the value of time t and calculate and equation 1 over t is equal to 5 over t. So we have 17.85, 5 over 17.85. This will give me 0.28. Remember, if all of the values are two decimal places, we'll keep it to two decimal places. Plot a graph of distance d against 1 over t. So remember, the first thing that you have to do is label the axis. So this is on y-axis, 1 over t slash 1 over seconds on x-axis. So this is what you have to write. It always carries one mark. Uh, then we have to select a scale. So we need to look at the values. They start with 20 and they end at 60. So 20, 40, 60 will be too short. 10, 20, 30, 40, 50. So if I start from, what I can do is start from 10 maybe, 20, 30, 40, 50, 60. So I'll be able to cover more than half of the graph, so this is fine. And for 1 over t, it starts from 0.28 and it ends at 0.88. So 0.2, 0.4, 0.6, 0.8. I think that should be fine if I use 0.2, 0.4, 0.6, 0.8, and 1.0. Starting off with the first point, at 20.0 we have 0.28. Remember to put a cross. Don't use dot, because when you draw a line the dots are usually not visible. At 30.0 we have 0.44, 0.42, 0.44. Then we have 40.0, 0.57, 0.5246, 0.57. 50 is 0.72 and 60 is 0.88. So 0.88. Determine the gradient. Okay. Plot a graph. So we'll use a line. We should draw one line. Don't connect all the points individually. You should draw one straight line and it should pass through most of the points. So this point is slightly below and these 2 points are above, so which is completely fine. They're not that far. um, so line is okay. About the f part, determine the gradient of the graph. Show clearly how you obtained the necessary information. Now if you want to find gradient, remember you have to be very clear in showing the points that you considered. So always try to take points uh, which are at the intersection. So I'll definitely take, let me use a black point, this as one point, and maybe I'll take this as the other. So you have to show a triangle like this. So a triangle does carry a mark, and if you want to label these points, you may. So this is 0.84 on x-axis and 57 on y-axis, and this one is 0.22 on x-axis and 16 on y-axis. So if I were to find the gradient, so we have to just use m is equal to y2 minus y1 divided by x2 minus x1. 57 minus 16 and 0.84 minus 0.22. So 57 minus 16, 0.84 minus 0.22. This gives us 31.19. We can just write it as 31, the gradient. G part 1, explain why it is more accurate to measure the time for 5 oscillations rather than for one oscillation. Um, so basically, I'll give you a complete logic. You have to write it in a short form, it's 1 mark. So for larger values of time, the error due to human reaction time reduces in percentage. So if we are measuring maybe 1.5 second, and that I have a reaction time of 0.2 seconds, so you do the math, that is a certain percentage. But if I have 10.5 seconds having the same reaction time, the percentage error will reduce. So this is what you have to write in these examples. So the error due to human reaction reduces in percentage, or in simple terms you can write the percentage error reduces. Describe how the experiment could be improved to make the readings more reliable. Reliability can be achieved if you keep on repeating and calculate the average value. That makes the experiment more uh, reliable. For each value of d, repeat the experiment and find average value. Question 2. Student investigates the cooling of hot water in two different cups. They use the apparatus shown in figure 2.1. Cup A is made from thin plastic. The top of cup A has inside diameter of 7 centimeter. Cup B is made from expanded polystyrene. The top of cup B has inside diameter of 8 centimeter. Fine. Record the room temperature shown um, on the thermometer in figure 2.1. So this is quite easy. It's 20, 21, 22, 23 degrees Celsius. Make sure you write the units. Describe one precaution um, that you would take to ensure that temperature readings in the experiment are as accurate as possible. So in situation like these, um, if you want to record temperature, it takes some time for the temperature reading to become stable. So there are different options, but if they're asking for one precaution, don't write two precautions. So what I will um, write is regarding wait for temperature reading to become stable before recording it. That is a precaution. Other precautions may be for experiment like these, we make sure um, the solution is uniform in terms of temperature distribution. So you have to stir before taking a reading, etc. A volume of 100 cm cube of hot water is poured into each cup, and initial temperature theta is recorded in table 2.1. The temperature of the water in each cup is recorded every 30 seconds. Values are shown in table. Fine, complete the headings in table 2.1. So we have to write the units. Time is in seconds, degrees Celsius, degrees Celsius. Write a conclusion stating which cup A or B is more effective in reducing the cooling rate of the hot water in this experiment. Um, Justify your answer by reference to the results. Reduce the cooling rate, so we can clearly see that cup B is more effective because we can clearly see the last temperature is 80.5. Cup B is more effective. The final temperature of cup B is 80.5. which is more than cup A, you can write 77.0 degree Celsius at 180 seconds. So this is just a simple statement we can clearly see. B has less heat loss compared to A. Calculate XA, the average cooling rate for cup A over the whole experiment using the readings for cup A from table 2.1 and the equation. So if we were to use this, where T is 180, theta 0 are the temperatures, fine. So at 0 it is 87.5, 180 it's 77, divide by 180. So 87.5 minus 77 divide by, so 0.0583, we can write it as 0.058. Then they're asking suggest an additional experiment to show how the lid affects the cooling rate of cup A. Explain how to use additional result to show the effect, additional experiment and explanation. So what we can do is we can repeat the experiment for cup A because A was using lid without the lid. So that will help us understand the difference, right? So we'll calculate the cooling rate. Fine. So this is what we are going to do. Uh, we'll calculate the cooling rate without the lid to see the difference between the two experiments. This is what we are going to do. We'll repeat cup A because this is what they did. Cup A is made from thin plastic, um, and cup B is made up of expanded polystyrene. So we wanted to know then, lid was there on both the cups, but the question was how to look at um, the effectiveness of lid. So we'll repeat the experiment without the lid and see the difference. Then we have a student wishes to compare the effect of the material of the cup on cooling rate. Suggest two variables that she should control to make this test fair. A very common one is it should have same initial temperatures for both cups and same volume of water should be used. Then we have question 3. A student investigates a resistor and a lamp connected in series. She uses the circuit shown in figure 3.1. Okay, so we want to investigate the resistance. The student moves the crocodile clip on the resistance wire so that the value of potential difference across the lamp is 2 volts. Fine, she measures the current I of for the lamp and resistor in series. She then connects the voltmeter to measure potential difference across the resistor. Read and record in table 3.1 the values of I and VR. Okay, so I in figure 3.2 is, this is 0.18. So we'll write 0.18. VR is 3.567, 3.7. So calculate and record the resistance. We did this. Use the value of VL and I from table and the equation RL is equal to VL over I to find the resistance RL. So we'll use 2 divided by 0.18. So that will be 11.1. And we'll use 2 divided by, calculate and calculate RL. So I'll find RL for all of them. VL over I. So 1 divided by 0.15, 6.67, and zero point 0.5 divided by 0.12, so 4.17. Use the values of VR and I to find RR. So I'll be using VR 3.7 divided by 0.18, that will be 20.6. 3 divided by 0.15, that will be 20. 2.4 divided by 0.12, that will be 20 again. Describe the pattern of any change in the values of RL and as VL decreases. So I can clearly see in this column RL decreases as VL decreases. So we have to just describe the pattern, we don't have to explain why. So as VL decreases, the RL decreases. C part 2 is the student suggests that RR should be constant. State whether your results support this suggestion. Justify your statement by reference to values from table 3.1. So if we look at the statement and justification, we think, yeah, it is same actually. RR is constant because if you look at the difference, you can even find the difference. 20.6 minus 20 divided by 20 into 100. So we can say the maximum variation, in values of RR is 3%. Then you have to kind of memorize this fact. If the percentage variation is less than 10%, we say it is consistent or it is supported, which is within limits of experimental accuracy. You can show the working over here. 20.6 minus 20 divided by 20.6 into 100, that is the percentage variation in R. So this is how you can find the percentage variation. A student wishes to determine the resistance of the lamp RL when the potential difference across the lamp VL is 0.0. Describe how the experiment can be extended to do this with the help of a suitable graph. So what we can do is we can have, for graph we need to have at least 5 values. Repeat experiment to obtain more values of RL against VL. Extend the line to the RL axis and read the value at VL is equal to 0. So this is what we are going to do. We are going to have like VL against RL, and if we have a graph like this, so we'll extend it, observe the value of RL at VL P at 0. So this is the point that we'll have to see from the graph. So anyway, this is D part. E is it is possible to use a variable resistor instead of resistance wire to change the potential difference across the lamp. Complete the circuit in figure 3.4 to show a variable resistor used for this purpose, the voltmeter connected to measure the potential difference across the resistor. So now we want to vary the resistance across the lamp, but we don't want Um, Over here we were using a resistance wire, but now what we'll be doing is we'll use a variable resistor. So we have to know the symbol of variable resistor. So it has to be the one with an arrow. So this is the formula, the symbol for variable resistor or rheostat. We don't need anything over here because it has to be connected in series, and they want a voltmeter across lamp. A student investigates the motion of a ball rolling down a slope. Plan an experiment which enables him to investigate how one factor affects the average speed of the ball. Average speed can be calculated using the equation. Average speed is equal to distance traveled by time taken. The apparatus available includes balls of various sizes and material, a board which can act as a slope, blocks to support one end of the board. In your plan, you should state a factor which can be measured. List any additional apparatus needed. Explain briefly how to carry out the experiment, including exactly which measurements are to be taken. State the key variables to be kept constant. Draw a table or tables with column headings to show how to display the readings. You're not required to enter any reading. Explain how to use the readings to reach a conclusion. You may draw a diagram if it helps to explain um, your plan. So we need to plan an experiment which enables to study one factor which affects the average speed of the ball. We have a board which can act as a slope. We have balls of various sizes that is fine and block to support one end of the board. So it's a 7 mark question, and we need to plan an experiment how one of the factor can affect average speed. So we have to identify um, an independent variable which can um, affect basically the average speed. So one of the factor that we can think of is if they have mentioned balls of various sizes and materials, we'll go for size or diameter of ball as the independent variable. So we can start with mentioning the factor which can affect average speed is diameter of ball. So dependent variable will be speed, independent variable will be the diameter of ball. It's a good practice if you talk about constants over here. We have to keep other factors constant. Now you have to come up with more of these factors which can affect average speed. One of the factor which I think of this slope is the um, angle of board and mass of ball, distance of ball on board. By that we mean the starting point. These are all the factors which have to be kept constant. So now we have to know how do we measure the average speed. Talk about average speed will be measured by measuring distance using a measuring tape from the initial marked position final marked position. The time taken should be measured by a stopwatch from initial to final marked position. The diameter of ball should be measured using a vernier caliper. It's an instrument which can measure diameters, etc. The experiment for at least 5 different diameter readings. Mark clearly the start and end of motion of ball. The ball should be released without any initial speed, just to make sure that human error is minimized actually. So this is what we are going to do. We don't have to, you may draw a diagram if it explains. So this is what I meant. We'll use a board. We have to keep this angle constant. uh, they talked about some support, so we'll use this support. We'll mark this position marked for the ball, and we have to label this as total distance, or we can even position marked over here. So we'll have to keep on repeating for different values of diameter. Let me call this distance with S because diameter is measured with D. So anyway, this is the idea. It will be a good practice if we write for each value of D, repeat experiment and find average D. So this is what we have to keep in mind, that um, 5 different experiments for D, and for every experiment we have to find um, the average time. So about the tables that we have to talk about, so we can say diameter centimeter, time 1 in seconds, time 2 in seconds, and then average time in seconds, distance in centimeters. um, we need to have a specific column for average speed as well. That is the most important. Average speed in meters per second. We have talked about distance, etc. as constant. Fill the above table for different values of D and plot a graph. So remember, dependent of average speed against diameter. So this is what we have to write in this experiment. Um, we talked about the variables, we talked about the apparatus, the factor, briefly experiment, draw, table, column headings, explain how to use the readings to reach a conclusion. Um, so, yeah, that we have to talk about. You can also mention the x's. Remember, the speed, if it is dependent, speed should be on y-axis and diameter on x-axis. If the graph is not a horizontal line, then it means the diameter does affect the average speed, or you can write a reverse argument.